Okay, now we want to talk about reflecting a line segment or triangle through two lines. So right here are 2 points and a line segment. We're going to reflect this line segment through this line, then through this line. Well, we just do this. We don't try to figure out what it's going to look like when it's all reflected. We just go point by point and construct the reflections. We first reflect this point through this line, right angle, equal distances. Then we reflect this point through this line, again at a right angle and hopefully equal distances. Okay, so we've reflected this line segment through this line. Let's label these points just so we can keep track. There's A, B, here's A prime, and here's B prime. Now we want to reflect this segment through this line. Well, we start, let's say, with B prime, and we reflect it straight across. And we get a point that I'll call B double prime. And then A will reflect across. And let's see, I have equal distances here, fairly good. Okay, so about here. So we'll call this A double prime. And here's our reflection. Now, A double prime makes some angle, A double prime, B double prime, this segment makes some angle with this segment. Okay, and we could actually figure out what that angle is. We can sketch that angle. Let's just extend the AB segment, and there's no reason that that should go through this point of intersection. That's just a coincidence. And we could extend this segment, and now we've got an angle here. Okay, this is, well, we have actually two angles where these lines cross. We have an obtuse angle on one side, and we have an acute angle on the other. And we might want to think about how these angles are related to this angle. I'm not going to do that analysis right now, just something to think about. Okay, so what's happened is the segment AB still has the same length when you reflect it once and then reflect it again, but here it's rotated. The segment AB has been rotated, and it's also been moved from here to here through some distance. So that when you reflect through a line, you do have a rotation. When you reflect through another line, you get another rotation. You get a net rotation when you reflect through two lines. Okay? And this intermediate rotation isn't, well, I don't want to talk any more about that. You get a rotation. Let's see how that works out. We'll see how that works out down here with a triangle. But let's now reflect this triangle through these two lines. First this one, then this one. Now I'm going to do this fairly quickly because this one's pretty straightforward, and I'm not going to do a whole lot of explanation. I'm just going to concentrate on getting good right angle here, here, and here. Bad start there. Okay, now let's see, equal distance, fairly good, fairly good. That one's a little too far. And let's say here. Okay, so we're not going to get a great result, but that's reasonable. This is a reasonable representation of the reflection. Again, this triangle got a little too skinny because actually I went a little too far when I did this point. This distance is a little greater than this distance. I'm not going to correct that. We'll just live with it. Now, if I reflect through this second line, well, I keep going. Okay? Then equal distance would put me about here. Equal distance would put me about here. and equal distance on this puts me about here. And here's my triangle. Okay? Now, this straight line here kind of deviated a little bit, so this point's a little bit too low. Not everything is exactly right, but it should be plausible to you. And if you do this carefully with straight edges and so forth, you can verify that this triangle is geometrically similar to this one. Now, this triangle is also geometrically similar to this one. They have all the same sides and same angles, but this triangle is in the same orientation. It's not flipped. So that in two reflections, what I do is I essentially flip the triangle twice, get it back to its original shape, and then I have a translation. This is called a translation. And the translation distance is from here to here. And that distance is the same for all points. Again, I'm not going to go through a geometrical proof of that, but that distance is the same for all points. So the distance from here to here is the same as the distance from here to here, is the same as the distance from here to here. If I label these, label the points A, B, C, A prime, B prime, C prime, then A double prime, B double prime, C double prime. The distance from A to A double prime is the same distance from B to B double prime, and that's the same as the distance from C to C double prime. Okay? Length of the segment, we'll just call those segments. Okay? So those distances are all equal, and everything is equal. So it's like we just took this triangle and scooted it over in this direction, let it glide over in this direction. Okay. Now, let's do the triangle through the two lines. Okay? And the lines are no longer at a right angle. So we get this, we get this, we get this, so we have this reflection, then we have this reflection, get the distances as closely matching as possible. Okay, so let's see. We got this distance, and that would put us down about here. So that our reflected triangle is again geometrically similar. That could be proved, but the triangle has been rotated. This side has gone to this side, has gone to this side. This side has reflected to this side, which is reflected to this side. This side is reflected to this side, which is reflected to this side. And we see that the triangle has been rotated. If we rotate this triangle about this much, it should match this triangle. Now we've, again, lost our exact triangle in doing this by hand. Every reflection, we tend to compound our errors, but we can see very plausibly how this triangle is a rotation of this triangle.